The cruel ogre wants to test a new invention that involves a device to lift a mass of 30 kilograms that is attached to a spring, initially compressed by the mass, with a spring constant equal to 15 newtons per centimeter. How much work would it take for the donkey to lift the mass by a height of 75 centimeters? So this is a pretty contrived looking example here. I just made it up to give us some practice with these ideas, really. I don't know why the heck someone would make a device like that. This example really fits pretty well the concept of work is equal to a change in energy. And we saw on the key concepts page that this was subdivided into a change in kinetic energy and potential energy, but I don't know if I need to worry about that necessarily so much here. But the thing, I'm going to actually look at if this represents the mass, and keep in mind we have a more detailed picture over there on the slide to the left. But maybe if this represents the mass initially, and then it's going to be lifted up by the donkey some height, right? And so here it is, some height above that. Again, not necessarily drawn accurately, but we're talking about, right, that displacement h there. Let me make that look more like an h. And the way I'd like to look at this is to recognize, I'd like to think about initial and final. Those are kind of really whenever we do energy, we're always comparing initial to final, kind of tracking a score from initial to final. But we're also kind of conceptualizing what we think is there initially versus what is there finally. And in that sense, initially here, I would say one of the things that makes this question kind of interesting is it does say initially the spring is actually compressed. In other words, I think there's going to be some amount of initial energy of 1/2 k x sub I squared, where I've just kind of invented a symbol x sub I here that was not actually given to me in the problem statement. K is given to me, right? But x sub I isn't. So I'm going to need to probably solve for that later on. But that's going to represent the initial compression that spring has, and I think that's going to be part of the initial energy. I'm going to assume that the gravitational energy is 0 where the spring starts. It's not exactly on the ground, but it's going to be easier for me if I assume that that's kind of 0 there, because that means in the final energy, I can associate a gain of gravitational energy by mgh. But I'm also going to assume that as this thing is lifted up, it's gone maybe from compressing the spring to stretching it. That may be a bit of an imaginative leap, but I think it's going to make sense. And so there's going to be some additional energy that needs to be provided for that. That's going to correspond to 1/2 k x final squared. In other words, the amount of energy that needs to be put into that spring to give it whatever final amount of stretch is represented by x sub f there. And again, x sub f and x sub I kind of had to put in on the fly here to get that to make sense. And my goal, of course, is to calculate how much work. So if I track this through, I'm going to say the work is equal to kind of final minus initial. And I look at it, though, kind of this mgh represents the change in gravitational energy, and then I'm going to add to that the change in the spring energy. In other words, symbolically, I could maybe have also looked at this system. Oops, that should be an I there. I could look at this system and say that we're tracking the changes in the different energy forms. Let me actually throw up here, because there could have been a change in kinetic energy, right? Do I have any of that here, right? But there was definitely a change in gravitational potential energy, and there was definitely a change in spring potential energy. And based on what I've written here, I think I've made the tacit assumption that there is no kinetic energy change at all. What does that actually correspond to? That means that the mass started at rest and ended at rest. Of course, it had to move in between, so maybe there was some kinetic energy involved there. But as long as it started at rest and ended at rest, I can safely say there is no change in kinetic energy. It started with 0, it wound up with 0. This one here, the change in the gravitational energy, that wound up being that mgh that I got there, and this wound up being I don't know if I should have written it this way, but 1/2 k x final squared minus x initial squared is equivalent to what I have over here. It's also worth saying that in all of this analysis, What is the system? Is the system simply the mass? The answer is no. You have to, if you want to associate energies with something in a system, you have to include appropriate things in the system for that. So, in other words, to associate gravitational potential energy, you need to have gravity included in your system, which is, again, it might seem a little arbitrary, but I'm just going to say that right now. We'll see a little bit later where that comes from in more detail. But I'm also going to say that the spring had to be in the system. Otherwise, I could think of the spring as being something external, and then maybe it would actually contribute to work. But the thing that's really external to this system is the donkey's pull. Maybe these pulleys, you could argue, well, are those internal to the system? Are those external? I think they're actually external, but their only role is to kind of transmit the force that the donkey applies to the system through the tension force over these pulleys. So in that sense, whether I do or do not include them, there's no real energy changes associated with them. So, okay, now I've got those formulas here. How do I proceed? Well, clearly H is equal to 75 centimeters. I'm just going to write that as 0.75 meters. Okay, so I've got that number. K is the spring constant, is equal to 15 newtons per centimeter. It turns out that's 1,500 newtons per meter. If you do the conversion on that, make sure you don't accidentally make it 0.15 newtons per meter, because that would be way too small. And we have mass sitting there as well, so we may as well make note that we have 30 kilograms of mass. However, we fall short on knowing what x sub f and x sub I are. So I think we're going to need to find those. So the way that I'm going to find x sub I is if I think about this mass when it's initially at rest, if I think about like an FBD for that, it's going to have its weight force, and then it's going to be pushed up on by the spring force. So that's the spring force. This should be a better G right there. Okay, for the weight force. I think if it's perfectly in balance there initially, just compressed by its own weight, that implies that the spring force in the form of Hooke's law, K times xi in this case, should be exactly equal to the weight, mg, which suggests that xi is equal to mg over k, which is calculable because we have mass. We know that g is equal to 9.81 meters per second squared, and we know k is equal to 1,500 newtons per meter. I've gone ahead and put that calculation into my calculator. Since I don't have a ton of space to work with here, I'm just going to write the result of 0.1962 meters, which might seem small, but that's 19.62 centimeters to put it in comparison to the 75 centimeters height. What is x final going to be? X final, really, I think it makes sense that x final might be equal to the total height it displaces through minus whatever initial compression it had, because it would first have to uncompress, and then the spring would stretch by whatever remains. That's the way I'm kind of looking at it. So that's really like, as a formula, would be h minus xi, which is also calculable. But with these numbers over here, I'm just going to write this way, because what I wound up doing in my calculator, rather than bothering to calculate what this is I just put this in as h. Hang on, this minus sign looks horrible there. Let me fix something here. Okay, h minus xi, that should have been, I think I accidentally made a mark there. Anyways, h minus xi, I'm going to put in for this, square it, minus the 1/2 k xi squared. And so now I can put, this is the new number I needed. That's going to go into xi here. It's going to go into xi there. And I don't know. I mean, I maybe have enough space to fit all that in, but I think when I start putting in all the numbers, it's going to get pretty crazy. So maybe I would just write down what result I got here, which was, 421.875. And that should be in joules. But I think that's going to round off to just 422 joules at 3 significant figures. So that's what I'm going to report as my final answer. Again, if you want to, you could write these formulas down and make sure you know how to do those calculations. I often encourage that, because it is not just important to know how to set up a question, but it's also important to know how to pull off the calculations. But there is that 422 joules as the answer.